Okay, so welcome back. Today what we're going to be doing is taking a look at the fields of a moving point charge. So last time we looked at the Leonard-Vickert potentials, and now we're going to be looking at the fields of a moving point charge, and I'd really say that this is another milestone in E&M. Okay, so back in P332, we had Coulomb's law, we had the Lorentz force law, and that gave us the E field and the force on a single point charge. And as we've seen in the last lecture, the Leonard-Vickert potentials gave the potential V and the vector potential A for moving charges. So what we're going to be doing is completing the job today, finding the full E and B fields for moving charges, and then in doing so we're going to be making a complete theory of electricity and magnetism that's applicable to statics and dynamics both. So it's really a true master equation for describing everything that can happen in E&M. So to begin, we're going to start from last time with what we have as the Leonard-Vickert potential. So we have that the Leonard-Vickert potential was written as V of R and T is equal to Q over 4 pi epsilon naught times curly R times 1 over the quantity 1 minus curly R hat divided into V divided by C. Okay, and then we can also say that that's equal to 1 over 4 pi epsilon naught times QC over curly R times C minus curly R vector divided into V. Okay, so that's our potential V. And then we can also say, once we know that our vector potential A of R and T is equal to the velocity vector V over C squared times the scalar potential capital V of R and T. Okay, so once we know V, then we know A, and those are the total Leonard-Vickert potentials. Now, I want to remind you that a few lectures ago, okay, actually when we started chapter 10 and we started looking at the potential formulation, we could also write down two expressions for the electric and magnetic fields purely in terms of potentials. So from before, we can say that the electric field is equal to minus gradient to the potential minus dA dt. And we can also say that the B field is equal to del cross A. Okay. So in principle, all we have to do, if our goal here is to figure out our E and B fields for our moving charges. Okay, so in principle, we know what V and A are. We know how to calculate E and B given V and A. So in principle, we just have to substitute V and A back into these expressions for E and B, and we're done. Okay, so that's all we have to do. But in practice, this gets a little bit tricky. Right, so the difficulty here is that our curly R vector, okay, the curly R that appears in these expressions for V and A as well, this curly R we can write as just the ordinary R vector minus W of T sub R, where this part here codifies the trajectory that our particle is taking. And in particular, this trajectory depends on this delayed time. Okay, so T sub R is equal to T minus the magnitude of R minus R prime divided by C. Okay, and this T sub R itself, as you can see, it is a function of R and T. Okay, so really what we should be saying is that curly R is really a function of R and T, and since curly R is a function of R and T, then we have to be really careful, because we implicitly then know that all of these curly R's are functions of R and T, and so when we come in and take these derivatives with respect to space or with respect to time, we have to account for the fact that there are also spatial and time dependencies hiding in that curly R as well. Okay, so it's not insurmountable, we're going to be doing it, but it's something that we have to take into account if we actually want to get the right answer. Okay, and so with that as our goal, then we can actually start going in and plugging away. And Griffiths actually does about 2 pages of heavy lifting for you. And if you go through the text, then you can actually follow every step. There are a lot of vector identities. There's a lot of just going carefully and brute forcing your way through the calculation. So I'm not going to rederive everything. It's in the text if you're interested. But the final result, taking care of all of those derivatives, making sure that we're accounting for the curly R dependence of R and T, then we end up with the result that the electric field as a function of R and T is equal to Q over 4 pi epsilon naught times curly R over curly R vector dotted into U, and I'll define that in a minute. So curly R vector over U cubed times C squared minus B squared times U plus curly R crossed into U cross A. Okay, so that's our total electric field. I've introduced a couple of new symbols here. Right, so in this expression, we have that U is equal to speed of light c times curly R hat minus the velocity v. And we have that the vector A, this here is our acceleration, so it's just defined as the vector v dot. Okay? So this is just our acceleration, time derivative of v velocity. All right, and so once we have the E field, then the B field, we can write down in terms of the E field. And we can just say that B of R and T is equal to 1 over C times curly R hat crossed with E of R and T. Okay, so what we've done is we've taken our known potentials, we've taken care to remember the time and spatial dependencies of curly R hat, we've substituted those in and calculated our E and B fields here. Okay? And what we've landed on is, I would say, a pretty remarkable result. Okay? So here, these are the total E and B fields of a moving point charge. And if I were to draw what's going on here, so let's say we have our particle. Okay, and let's say at some instantaneous time, the particle is here, and it's really moving with some velocity v to the right. Okay, so our particle is moving along, and what we found for these fields is that both the E field is now perpendicular to the B field, which is also perpendicular to the vector direction curly R hat. And so we have, I'll write it down here, that B is perpendicular to E, and it's perpendicular to the vector curly R hat. Now remember, the vector curly R hat points from the point where the particle was at that earlier time to the point of interest. Okay, so your point of interest might be over here, right? So curly R hat actually points from the particle's position at this delayed time to our point of interest up here. Okay, and then we have that the E field is perpendicular to that, and then the B field, which in this case would be out of the board, is perpendicular to the E field as well. Okay, so we have this remarkable result that if you wanted to calculate what the E and B fields were at a particular time, then you have this mutual perpendicularity, just like we had for free electromagnetic waves traveling through space, and then the directions to which they are perpendicular point back to the retarded position of the particle. Okay, and so next what I want to do is look at those expressions a little bit more closely. And I want to sort of build ourselves up. So the expressions that I just erased, they are a little bit big and unwieldy. And so I think it will help build some intuition if we're able to look at them in some reduced cases first. Okay, so the first case that I want to look at is somewhat of a simplified one. Okay, and so that's just when the velocity is equal to the acceleration, which is equal to 0. Okay, and another way to say that is just that we have a stationary charge. Okay, so if we have a stationary charge, and we plug in V is equal to A is equal to 0 into our electric field expression, then we have that E of R and T is equal to Q over 4 pi epsilon naught times curly R over curly R vector dotted into U vector cubed. And then in brackets, the only terms that we have remaining are a C squared U. Okay, but if we look at our definitions from just a few minutes ago, we have that the vector U is equal to C times curly R hat minus the velocity, which is 0 in this example. Okay, and so that's just leaving us with a C times a curly R hat. And so with that definition for U, then we recover that the electric field of R and T is equal to Q over 4 pi epsilon naught times curly R over curly R vector dotted into C curly R hat cubed times C squared times C curly R hat. Okay, so I've just substituted for U everywhere. And then we see we have a C cubed here, a C cubed here. We have an R hat and an R hat. Okay, and really all this is going to leave us with is a Q over 4 pi epsilon naught times curly R hat over curly R squared. Okay, and this should really look familiar. This is our normal, in quotes, this is our normal Coulomb potential. Really, I should say normal Coulomb electric field. Okay, it's the electric field that we saw within the first weeks of P331, right? Just a stationary charge. We have this ordinary looking electric field that comes off of a point charge. So our complicated electric field in the limit of no velocity, no acceleration reduces to something that we'd expect. Okay, so we're on the right track. Now, one of the things, this is also just an aside, if you go back to our expression before for the electric field, okay, and maybe I can write this back up. So from before, we had that our total electric field of R and T is equal to Q over 4 pi epsilon naught times curly R over curly R dot U cubed times C squared minus V squared times U plus curly R crossed with U cross A. Okay, and so as my aside, what I really want to point out in this electric field is that this first term here, if you look at its prefactors, you have an R in the numerator and an R cubed in the denominator. So the first term goes like 1 over curly R squared. Now the second term here, we have an R over R cubed, but then we have another factor of R in the numerator. And so we can actually say that this acceleration term in total just goes like 1 over R. Okay? And it's this acceleration term that dominates that large R. Okay? So if you're really far away from a moving point charge, then it's really this acceleration that's going to contribute most of the electric field, okay? Not this other term here, right? And so we're actually going to start to see that in the next lecture, and as we go into chapter 11, when we start talking about radiation, that by and large, all of the radiation that we care about in physical systems is driven by this kind of acceleration, because it's the largest contributor to the electric field as we go far away from the source. Okay, so I want to point that out, and you should remember that that is coming in the future, and it all comes from this expression for the electric field, that the acceleration is proportional just to this 1 over R term. Okay. So now that we have expressions for our total electric and magnetic fields of a moving point charge, I want to bring us back to something else that we've seen. And this again is early on in the course, which is the Lorentz force law. Okay. So we can always say that the Lorentz force law, we can say that the force is equal to, let's say, capital Q times E plus, I'm going to call it a capital V vector cross B. Right? And this is the force on a test charge, call it capital Q, moving with a velocity capital V. Again, I'm using capital V here because I want to distinguish it from the lowercase v, which is some other charge that's creating the electric and magnetic fields in the first place. Okay, so we can say that the force is capital Q times E plus capital V cross B. We had E and B before, which are the fields from the moving point charge. Okay, and so in total, we can then say that the total force on this test charge is equal to little q times big Q over 4 pi epsilon naught times curly r over curly r vector dot u quantity cubed times, okay, and here it comes. We've got c squared minus v squared times u plus curly r cross u cross a plus capital V over c crossed with curly r crossed with c squared minus v squared times u plus curly r vector crossed with u cross a. Okay, and I close off all of my brackets there. Right? So that's really quite the expression. And just as I've said before, this velocity capital V and this charge capital Q, those are from the test charge. And then the curly r vector, the little u, the little velocity v, and the acceleration, those are all due to this moving charge that's creating the electric and magnetic fields in the first place. Okay, and so really all of electromagnetism, okay, statics, dynamics, anything that you can conceive, really it stems from this equation. Okay, so if you know your electric and magnetic fields, and we do as of a few minutes ago, if you know the force that acts on a particle due to those electric and magnetic fields, and we've just derived this expression now, then you can absolutely calculate anything else that's out there in electricity and magnetism. Okay? And so I could have, at the very beginning, lecture 1, P332, we talked about the Lorentz force law, I could have shown you this equation. I think it's pretty clear why I did not show you this equation. Everybody would have dropped immediately. Okay, but now we're finally at this level of sophistication that you can see where all of the terms of this Lorentz force law are coming in from. Okay, it's really just QE plus V cross B, just like we had before, but now we're sensitive to the fact that E and B depend on the particular trajectory of this new particle that's moving through space. Okay, and so with our E and B fields, I told you that I wanted to continue going on and looking at different cases. So we have looked at the case where we have V equals 0 and the acceleration is equal to 0, and that was just a stationary charge, and that led to the normal Coulomb electric field. Okay, so next is our next example. I want to look at a charge moving with constant velocity. Okay? And in this case, the acceleration is still equal to 0. Okay, so we just have a uniform motion, constant velocity charge moving, and we're interested in the electric and magnetic fields. So from our equation for the electric field, so we can, with a constant velocity and 0 acceleration, just say that the electric field is Q over 4 pi epsilon naught times C squared minus B squared times curly R over curly R vector dot U vector cubed just times the vector U. Okay, and again, we're defining U vector as C times curly R hat minus the velocity. Right, so that's our electric field. And we can make this substitution for U back into this expression and complicate it a little bit, but I want to go a bit further, okay? I really want to just deconstruct this thing piece by piece and see if we can learn something a little bit more physically intuitive about it. So let's deconstruct this thing piece by piece. All right, to begin, what I want to do is just really look in the numerator. Okay, so C and V here, these are just numbers, so there's nothing to deconstruct there. But we do have this curly R times the U vector. Okay. So we have curly R times U vector in the numerator, and given our expression for U, this is equal to C times curly R vector minus curly R times the velocity vector. We can write that as C times R minus V times T sub R minus C times T minus T sub R V. Okay. And this just comes from our definition of this vector curly R, which involves this delayed time here. And then combining like terms, we can say then that curly R times U is just equal to C times R minus Vt. Okay, so we've got a bit of a simplification here in the numerator. We've gotten rid of the U, and we've put things just in terms of R and V and T. Okay, so far, so good. All right, so the next thing that I want to look at is this denominator here. Okay, so in the denominator, we have a term that is R vector dotted into U, right? In the numerator, we just had the magnitude of R times U, and in the denominator, these are both vectors, and we're taking the dot product. Okay, so we can write that R vector dotted into U vector, we have that that's equal to curly R times C minus curly R vector dotted into V. Okay. And actually, I want to remind you that we solved for this last time. Okay? So last time when we were calculating the Wiener-Vickers potentials, we had this exact expression in the denominator. Okay? We spent a bit of time actually calculating what this would be equal to, and we can really just copy and paste that solution right now. Okay? And so we have that this denominator was equal to the square root of C squared T minus R dot V, quantity squared, plus C squared minus V squared times R squared minus C squared T squared. Okay, kind of a big expression. All right, so we've got this entire denominator. Okay, so this R dot U term becomes this square root, and then we're going to have to take the cube. But I actually even want to go a step further and simplify what's in here some more. Okay? And so to start, I actually want to call everything underneath this square root. Just let's define all of this stuff as S. Okay? And we're calling it S for stuff. And so really what this means is that we're saying that for now, just curly R dot U is equal to square root of S, because I don't want to write that over and over again, and I doubt you want to write it over and over again. Okay. So with this definition of S, we'll come back to it, but we just have that R dot U is equal to square root of S. Okay, and so if we were to expand, we could find that all that stuff, s, the thing underneath the square root, is equal to c to the fourth times t squared minus 2c squared t times r dot v plus r dot v quantity squared plus c squared r squared minus c to the fourth t squared minus v squared r squared plus v squared c squared t squared. Okay, nothing hard, just going term by term and being careful to get all of the terms in that expansion. Okay. And now if you look at this, we have a couple of cancellations, right? We've got a c to the fourth t squared minus c to the fourth t squared. Okay, and so we can combine some terms and simplify this a little bit to r dot v quantity squared plus c squared minus v squared times r squared plus c squared times vt quantity squared minus 2c squared r dot v times t. Right, so that's our expression for s. And the next key here is to look at the geometry. Okay, making reference to actually what's going on physically in this system is going to help us bring us that last little bit and simplify that expression. Okay, so in our geometry, we have a particle, charge q, and it's moving with some constant velocity v. Okay, and so if we have a point up here, we can define a vector, capital R. Okay, so I want to define capital R as equal to little r minus vt. Okay, and so this is the vector from the present position to our point of interest which is located at the vector lowercase r. Okay, so our charge is at this position. We're defining capital R to be lowercase r minus vt. Okay. And then one additional thing that we can do is define an angle theta, which is the angle between that vector r and the velocity vector. Okay. And so with this definition, then this expression for s simplifies even further. Okay, so with that definition, then s we could just write down as capital R dotted into v, quantity squared, minus capital R squared v squared plus c squared times capital R squared. Okay. And all I've done to do that is to imagine rearranging here, capital R plus vt is equal to lowercase r, and then I made that substitution everywhere in that expression. Okay, so our s is simplifying quite a bit, and then we can recognize that this term here, this r vector down into v vector, we can always write that as the magnitude of r times the magnitude of v times cosine of the angle between them. Right, so really this term, r vector dot v vector squared, we can just write as r squared v squared cosine squared theta. Okay, so things are really starting to simplify here. And it gets even better, right? You can feel another cancellation coming on, because we've now got an r squared v squared cos squared theta that goes right here. Then we're going to subtract off r squared v squared. All right, and we're going to get something that looks even a little bit nicer. So all of our stuff, S, we can write as r squared v squared times cos squared theta minus 1 plus c squared r squared. Okay, and so this cosine squared theta minus 1 is equal to minus sine squared theta times r squared v squared plus c squared r squared. All right, and then finally, I can write that S is then equal to c squared r squared. I'm factoring out a common term for both parts here, and then that just leaves me with a 1 minus v squared over c squared sine squared theta. Okay, and then finally I claim that we took that really awful looking expression, and finally we have something pretty palatable. Okay, so now we can start to build all of our pieces back together. So all together, we have that curly r vector dot u vector. We call this the square root of stuff S. Okay, and now we have our expression for S. So now we have that r vector dot u vector is just equal to c times capital R times the square root of 1 minus v squared over c squared times sine squared theta. All right, and that was the denominator of our expression. And then we have to cube that, combine it with the other parts in the numerator. And so in total, we now have, for a constant velocity particle, that the electric field is q over 4 pi epsilon naught times c squared minus v squared times c times r minus vt over cr cubed times 1 minus v squared over c squared sine squared theta to the 3 halves. And then as the final last little thing, we notice that this combination of little r minus vt, which is exactly as what we had defined to be the capital R vector. And so this whole thing we can write as q over 4 pi epsilon naught times 1 minus v squared over c squared over 1 minus v squared over c squared times sine squared theta all to the 3 halves times capital R hat over capital R squared. And there it is, the electric field from a moving point charge at constant velocity. Okay, and one of the really neat features of what we've just derived is that if you look at that expression for the electric field, and I've left it in the box there, the vector direction of this electric field points in the capital R hat direction, which, if you remember our geometry, capital R hat points from the present position of the particle. Okay. And so if we had this picture, right, so here's our velocity of the particle, here is the present position of the particle. Okay, all of the electric fields lines that emanate from that particle, they point from the present position of the particle outwards. And so the total electric field lines, they look something like this. Okay, so they're all emanating from the present position of the particle, and I've actually, drawn this sensitive to the fact that we have this extra sine squared theta now in the denominator. Okay, and so really what this means is that the E field lines, I'll say condense or flatten out, however you want to think about it. They kind of crush together perpendicular to the direction of motion. Okay, so there is actually an enhancement of the electric field perpendicular to that velocity, and that's driven by this sine squared theta in the denominator. Okay, and the effect gets greater and greater as this velocity gets closer to the speed of light. Okay, and so we can look at that in a couple of test cases. Right, so I will leave that expression there. say that as the velocity approaches the speed of light, okay, so as v is coming up close to c, right, then that denominator is kind of going towards 0. And we can also say then that along the direction of motion, right, so the direction of motion is where that angle between r and v is going towards 0. So theta is going towards 0, and we have that the electric field is approximately q over 4 pi epsilon naught times 1 minus v squared over c squared. And then if theta is going to 0, and hopefully theta is going to 0 faster than v is going towards c. Okay, so if we're really looking right along the direction of motion, and this denominator here just gives us a factor of 1. And then we have an r hat over r squared. Okay, and if v is going towards c, then this numerator is going towards 0. And this whole thing goes to 0 as v goes to c. Okay, so along the direction of motion, as you're getting close to the speed of light, then you have a suppression of the electric field. And then just the opposite is true when we're perpendicular. Okay, so in the perpendicular direction, then we have that our electric field is q over 4 pi epsilon naught times 1 minus v squared over c squared divided by 1 minus v squared over c squared to the 3 halves. Okay, in the perpendicular direction, this means that theta goes to 90 degrees here, and sine squared of theta is just equal to 1. Okay, so we have this expression times r hat over r squared. Okay, and then we get a nice cancellation right here. So we can say that this is equal to q over 4 pi epsilon naught times 1 over 1 minus v squared over c squared to the 1/2 times r hat over r squared. And again, this expression goes to infinity as v approaches the speed of light. Okay, this denominator goes to 0, and the entire thing blows up as v is going towards the speed of light. Okay, but if v is not going towards the speed of light, so if v is much, much less than c, right, then look what we end up with. If v is much, much less than c, then this 1 dominates here, and we just have that the electric field is equal to q over 4 pi epsilon naught times r hat over r squared. Okay, and once more, we have the Coulomb electric field. Okay, and so if v is much, much less than c, then all of our electromagnetism kind of looks like a stationary charge, at least at first order. Although when we go to higher and higher orders, if we want to start looking at corrections to this electric field, then we have to be sensitive to the fact that there is a little bit of an enhancement perpendicular to the motion, and there's a little bit of a decrease in the strength of the electric field along the direction of motion. Okay, so with that, we are finally at an end. These are the total electric and magnetic fields that we've talked about for a moving point charge. Next time, when we come into lecture, then we're going to start talking about radiation effects, okay, in Griffith's chapter 11. If you like this video, please subscribe. I'll see you on Monday.